A metal sphere in a spherical shell. A metal sphere with radius r sub a is supported on an insulating stand at the center of a hollow metal spherical shell with radius r sub b. There is charge plus q on the inner sphere and charge minus q on the outer spherical shell. So we have a metal sphere with radius r sub a. It's a solid sphere and a hollow metal spherical shell with radius r sub b. So the inner sphere has charge plus q and the outer sphere has charge minus q on the outer spherical shell. All right, part A, calculate the potential V as a function of radial distance r from the center of the inner sphere for the three cases r less than r sub a, r between r sub a and r sub b, and r greater than r sub b. And the net potential is the sum of the potentials due to the individual spheres, and we take the reference point to be r is equal to infinite for the zero potential. And in part B, show that the potential of the inner sphere with respect to the outer is VAB, that is equal to Q over 4 pi epsilon 0, 1 over R sub A minus 1 over R sub B. So we have two metals. We have a metal sphere, radius R sub A, and we know that in metals, the charge resides on the surface of the metal. So for this spherical solid sphere, we will have the positive charge, charge plus Q, residing on its surface because the electric field inside a metal is zero. And for the hollow sphere, spherical shell, we have the charge also residing on the surface. Well, it's basically empty shell, so it's going to have all of its charge residing on its surface, and all of this is on an insulating stand. All right, and the radii are r sub a and r sub b, and I will progressively consider Gaussian surfaces with different radii. So for example, for the first case, I will consider a Gaussian sphere with radius r less than r sub a. Now, the problem suggests that I can think of the net potential as being due to the sum of potentials of the two spheres. So if I isolate the two spheres, now I have a positively charged spherical metal sphere that's positively charged. All of the charge resides on the surface. Now I have a hollow insulating or metal, it doesn't matter. Actually, they will give the same result because it's hollow. All the charge is on the surface. So for both of these cases, I will have all of this charge on the surface because it's hollow. There's nothing inside, so there's only a surface here. And the charge it has is minus Q. So if I talk about the potential for R less than R sub A, so let's start with part A here. Okay, so I'm concentrating on the metal sphere. For R less than R sub A, if I consider the Gaussian sphere inside, I know that since all the charge resides on the surface, I have, this is for the case of a metal sphere, I have the charge enclosed by this Gaussian sphere, which is this sphere here, all of the charge is on the surface, there's no charge inside. So the Q inside is going to be equal to 0. And if I write Gauss law, closed surface integral E dot dA is the electric field only a function of radial distance r, and parallel to the area vector. The area vector is 4 pi r square in r hat direction. This is charge enclosed divided by epsilon 0, which is 0. So electric field inside the metal sphere is 0. Now, on the other hand, the electric field is related to the potential as minus gradient of the potential, and this is 0. So the gradient of the potential is 0, implies that for r less than r sub a, potential V of r is a constant. It must be a constant. Its gradient is equal to 0. So we can say that potential as a function of r for r less than r sub a is equal to the potential at the center. Now, what is the potential at the center? It is integral k dq over r sub a, because for each charge element that I consider here with charge dq, it is at the same distance r sub a from the center. So I add up the contributions from all of these point charges. So I will end up with kq over r sub a as the potential inside this metal sphere. All right. So on the other hand, for r greater than r sub a, the charge enclosed will be equal to q. So if I write Gauss law again, the closed surface integral E dot dA, this is E times 4 pi r squared. Charge enclosed is q divided by epsilon 0. So I will find that there is an electric field which is kq over r square. Actually, it's in r hat direction due to the positive charge in plus r hat direction. And the corresponding potential will be potential at r with respect to infinity minus the potential at infinity is minus the integral going from infinity to r kq over r square r hat dot dr r hat. And then I will find that the potential V of r greater than r sub a is equal to, because the integral of kq over r square is minus kq over r, minus signs will cancel. This will be just kq over r. So kq over r for r greater than r sub a. And it's going to be a similar situation for this hollow metal spherical shell. Inside, it's going to be kq over r sub b. Outside, it's going to be kq over r. So I learn from this calculation that for a solid metal sphere, or spherical shell, doesn't matter which one I use, or a spherical shell, the potential is V of R is equal to KQ over the radius R of the sphere. R is the radius of the sphere. Okay. This is for R less than capital R, and V of R is equal to KQ over R for R greater than capital R. Now applying it to this problem, I find that for R less than RA, we are inside both of these spheres. So potential as a function of R less than RA, the potential due to this one, this metal sphere, is KQ over R sub A. That is the potential inside the sphere, KQ over R sub A. And the potential due to the spherical shell will be minus KQ over R sub B, the radius of this one. So if this has charge Q, it's KQ over R sub B inside, but if it has minus Q, it's minus KQ over R sub B is the potential inside with respect to infinity. So I find that this should be the potential for the region with radial distance R less than R sub A. I could have basically reached the same conclusion by looking at the potential due to point charges here as well. So if I take another point charge here, at the center, this creates k dq over r sub b. Integrating it over the whole surface, I would get kq over r sub b, but it's a minus sign, so minus kq over r sub b at the center. Here it's plus kq over r sub a. Because the potential inside the metal should be a constant, then I would say that this is equal to the potential kq over r sub a minus kq over r sub b. So that's the answer to the first part, the first region, basically, that is r less than r sub a. And it's going to be easier to see what will happen in the other regions just using this superposition principle. So that's the answer to part I. Now, I can also say that similarly, I could have used the potential at r is equal to 0 is integral k dq over r, which is going to be equal to kq over r sub a minus kq over r sub b, considering both regions. And at the same time, potential is a constant inside a metal because the electric field is 0. Now looking at the second region, we are concentrating on a radial distance R between R sub A and R sub B, if I use the superposition principle, I would say that potential at R greater than R sub A less than R sub B is the potential outside a metal sphere. The potential outside the metal sphere is kq over r. So the contribution from the inner metal sphere would be given as kq over r. And the contribution due to the outside hollow spherical shell, because inside this hollow spherical shell, the potential is minus kq over rb. So this is just minus kq over r sub b. So this is the answer to the question for this region. But similarly, I can see the same result using Gauss law. Or I can say, if I write Gauss law, closed surface integral E dot dA. In this region, what is the charge enclosed by a spherical surface? So if I consider this Gaussian sphere in this region, so let's make it bigger. All right, so in this region, if I consider this Gaussian surface, the charge enclosed by this Gaussian surface is now plus q. So writing Gauss law here, I would have integral, closed surface integral E dot dA is equal to the charge enclosed q divided by epsilon 0. And that gives me E times 4 pi r square is equal to q over epsilon 0, and the electric field inside then must be equal to kq over r square in r hat direction. Now, potential at r, V of r, with respect to the potential at r sub a, V of r minus V of Ra, is minus the integral, the path integral, from r sub a to r, E dot product with displacement, and that gives me minus the integral from r sub a to r, kq over r square dr. And this gives me kq over r, evaluated between r sub a and r. This is kq over r minus kq over r sub a. Now what is this? This is the potential V at r minus V at Ra. What is the potential at Ra? It is kq over Ra, so with the minus sign this becomes minus kq over Ra plus kq over Rb is equal to kq over r minus kq over Ra. So these kq over Ra's will disappear from both sides, and I will be left with the potential for this region, V of r between Ra and Rb, to be equal to kq over r minus kq over r sub b. The same answer. Okay, so using the superposition principle, knowing the result for an individual metal sphere or spherical shell. So here I consider inside a metal spherical shell. Here I consider outside a metal sphere and add up the contributions from both. Or using a Gauss law, I can find the electric field inside, and using the electric field, potential at R minus potential at RA is minus the path integral R sub A to R, dot product of electric field with displacement. That also gives me the same potential difference. So that's the answer to the second part. Now, if I consider the region, the third region, R greater than R sub B, then I have a very simple situation, potential R greater than R sub B. What is the potential outside a metal sphere at a radial distance R from its center? It is KQ over R. And for the spherical shell, it is minus KQ over R. So these basically cancel out, giving me an answer 0. So I find that the potential should be equal to 0. Or I can say that if I consider a Gaussian surface outside of which encloses both of these, so let's change this color again for this Gaussian surface. Now this encloses both of these, this Gaussian surface. What is the charge enclosed by this Gaussian surface? It's going to be plus Q minus Q, 0. So the total charge is 0. If I write Gauss law here, closed surface integral E dot dA is equal to 0 because charge enclosed is 0. So that means the electric field is 0, which is minus gradient of the potential. Therefore, the potential at R greater than RB must be equal to the potential at R equals RB. It's a constant. So what is the potential at R equals RB? It is KQ over RB minus KQ over RB, which is 0. So this gives me KQ 1 over RB minus 1 over R sub B, which is 0. So I get the same answer. So the answer to this question then is potential for R greater than R sub B is equal to 0. So I have the answer for all three regions. I considered 3 Gaussian surfaces, inside, in between, and outside. I also used the superposition principle. I looked at the potential due to the single metal sphere. Inside, the potential is a constant equal to the potential at the center, which is KQ over RA. Outside, it is KQ over R. For this one, it's similar. It's minus KQ over R sub B inside, and it's a constant because the electric field is 0. Outside, it is KQ minus KQ over R. Now, in part B of the problem, we want to show that the potential of the inner sphere with respect to the outer sphere is Q over 4 pi epsilon 0, 1 over RA minus 1 over R sub B. So let's do that. In part B, potential AB, which is potential at R sub A minus the potential at R sub B is potential at R sub A. Why? Because we have shown that the potential at R sub B must be equal to 0. It is kq over rb minus kq over rb. So I can write VAB is equal to VA minus VB, potential at A minus potential at B, equals to potential at A. What is the potential at A? It is kq over r sub A minus kq over r sub B. Or here, if you substitute r is equal to r sub A, kq over r sub A minus kq over r sub B. Or if you substitute r sub B, you will get 0. Actually, here I could say that this is less or equal to, because they give the same answer. This is greater or equal to and less or equal to. And also for this one, this is greater or equal to r sub b, because at r sub b I will obtain 0 potential. So this basically implies that my answer is kq one over r sub a minus 1 over r sub b. All right. Now what is k? It is 1 over 4 pi epsilon 0. So this means that this potential VAB is equal to 1 over 4 pi epsilon 0, 1 over RA minus 1 over R sub B. And that's the suggested answer. That's the answer I was looking for. Potential of A with respect to B is 1 over 4 pi epsilon 0, 1 over RA minus 1 over RB. So that's the answer we were looking for in part B of this problem. Okay, so we have looked at the potential in 3 different regions: inside the metal sphere, in between the metal sphere and metal spherical shell, and outside the metal spherical shell. By considering the contribution from a metal sphere, knowing that the electric field inside is 0, the potential is a constant, and the potential inside is the potential at the center, which is kq over RA, and outside the potential is kq over R. So inside this sphere, we will have kq over R sub A due to this charge, and minus kq over R sub B due to the outer spherical shell. So that will be the potential, constant potential inside. And when I go outside, the potential due to this sphere is kq over R, but since I'm still inside this one, it is minus kq over RB. So kq over R minus kq over RB due to this one. And outside, it is kq over R due to this one also. So it is kq over R when I'm at a radial distance R, kq over R. I'm at a radial distance R, it's minus kq over R due to this spherical shell. So the outside potential will be equal to 0. Also using Gauss law, there is no charge for this spherical surface. Enclosed by the spherical surface, electric field is 0 inside. For this spherical surface, there is charge q, so it's kq over r square in r hat direction, the electric field. And outside here, I'm going to have no charge enclosed again, so plus q and minus q. That means the electric field outside is 0. Potential is a constant, and it's equal to the potential at r is equal to r sub b. And if I look at the potential difference between A and B, Looking at my answers, I see here the potential at R is equal to R sub A is KQ over RA minus KQ over RB. Potential at R sub B is 0, so it is KQ over RA minus KQ over RB is the potential of the inner sphere. It's the potential of the inner sphere with respect to the outer sphere. So it's VAB or VA minus VB. And for K, Coulomb's constant, we can substitute 1 over 4 pi epsilon 0.